For 13.8 billion years, no telescope has ever seen them. The very first stars. The ones made of nothing but the breath of the Big Bang. No human, no instrument, no observatory in history has ever caught one in the act of shining. Until last week. In April 2026, two independent teams of astronomers, one at Cambridge and one at Florence, used JWST to capture what may be the strongest evidence ever recorded for the first generation of stars in the universe. Population 3, the original ones, made of nothing but hydrogen and helium, because that is all the universe had yet built. They found them clustered around a tiny smudge of light next to one of the oldest galaxies we know. The smudge is so faint, it took the most powerful space telescope ever built, staring at the same patch of sky for hours, just to confirm it was there. And they gave it a name. I will tell you that name in about 3 minutes, because the name is not the headline. The headline is what is missing from the light this clump sent us. After travelling for 13.4 billion years to reach Earth, the spectrum from this tiny patch of sky is missing something specific. And that absence is the entire reason this discovery may rewrite the first chapter of cosmic history. Think about what you are made of. Every atom of carbon in your body, every atom of iron in your blood, every atom of oxygen in the air you are breathing. None of it existed at the start. All of it was forged inside stars, scattered by their deaths, and recycled into the next generation, and the generation after that, and after that. Every star ever observed was built on an older one, except the very first, the ones with no parents, and the ones that had to make everything out of nothing. To understand why this clump of light matters, you need to understand where it lives. Its host is a galaxy called GN-Z11, one of the most distant galaxies ever confirmed by humans. Its light has been travelling toward Earth for 13.4 billion years, which means we are looking at it as it was just 430 million years after the Big Bang. For most of cosmic history, GN-Z11 has been the brightest known beacon at this depth, a point of reference for everything astronomers know about how galaxies looked when the universe was very young. Astronomers have been studying GN-Z11 for years. But in 2024, when Roberto Maiolino and his team at the University of Cambridge pointed JWST's near-infrared spectrograph at the region around it, they noticed something they had not expected. Like there was a faint signal coming from a tiny clump of light just outside the main galaxy, about 3 kiloparsecs away. To put that in scale, 3 kiloparsecs is roughly the distance from our Sun to a star you might trace with binoculars in the constellation Cygnus, but scaled up across the early universe. The signal was strange. It carried the chemical fingerprint of doubly ionized helium. To produce that fingerprint, you need radiation so energetic that ordinary stars cannot make it. You need something extreme. Something hot. Something the universe had only ever managed to make once, theoretically, at the very beginning. The 2024 observation was tentative. The signal was faint. The instrument was new. The team flagged it as a candidate, a strong hint, and waited. In early 2026, deeper observations came back. This time, and the helium signal was confirmed at much higher resolution. Then a third paper, by a team led by Hannah Ubler, picked up the matching hydrogen line at exactly the same location, at exactly the same redshift. The signal was real. The clump was real. And whatever was inside it was producing a kind of light that, until that moment, no one had ever directly observed. The team gave it a name. Hebe, helium Balmer emitter technically, a made-up acronym folded around an old name. In ancient Greek myth, Hebe is the goddess of youth, the daughter of Zeus and Hera, the one who serves the gods their nectar of immortality. She is the embodiment of beginning, of the first morning of everything. The team chose the name carefully, because if they are right about what they are seeing, Hebe is not just a clump of light in the halo of a galaxy. It is the first morning of the universe itself, the moment before anything had been built, the morning before every atom in your body existed. That is what she has been named to hold. Here is what you need to know about chemistry to feel why this matters. Right after the Big Bang, the universe contained almost nothing. Hydrogen, helium, a trace of lithium, that was it. 3 elements. Everything else on the periodic table, every atom of every other element you have ever heard of, had to be built later. Inside stars, by nuclear fusion, and then scattered out into space when those stars died. Astronomers have a word for everything heavier than helium. They call them, all of them together, just metals. Carbon is a metal, oxygen is a metal, iron is a metal. In astronomy, the word means anything that had to be cooked inside a star. So if you find a star anywhere in the universe, made of anything other than just hydrogen and helium, you know it cannot be one of the first ones. It has been contaminated. Some earlier generation of stars made the metals it contains. And every single star ever observed, no matter how distant or how ancient, has shown some trace of metals. Always a fingerprint of a previous generation. The first generation, the one with no parents, had only ever existed in theory, in simulations, on whiteboards, as a category we knew had to exist, but had never been able to point to, until Hebe. When the team analysed Hebe's spectrum, they looked for every metal line a normal stellar population should emit: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron. They found none. And the upper limits were so tight that the team's models could only reproduce what they saw if more than 50% of the stellar mass inside Hebe was made of pristine, metal-free stars. The 2 lines that are present, helium and hydrogen, are exactly what these stars should produce if they exist. Hot, pristine, burning so violently that they double ionize their own helium gas. The fingerprint matches what theory predicted. Think of it this way. Imagine you walk through fresh snow and find a single footprint. Just one. Crisp, perfectly formed, sitting in the middle of an unbroken white field. No path leading in, no path leading out. The print is real. You can measure it. But the absence of every other track is what tells you that whatever made this print was here, and only here. That is what Hebe's spectrum looks like. And helium and hydrogen say these stars are real. The absence of everything else says these stars are first. There is nothing before them. They are the start of the chain. If you want more of these stories while they are still breaking, subscribe to Cosmic Tide. We are only just getting started. Now, if you have never thought about this before, you might assume the first stars looked roughly like the stars we see today. A range of sizes, some small, some big, mostly something in between. The Sun, for instance, sits comfortably in the middle of the modern stellar size distribution. There are stars smaller than it. There are stars bigger. The Sun is unremarkable, statistically speaking. The first stars were not like that. In a universe with only hydrogen and helium, gas behaves differently than the gas we see in the modern Milky Way. A modern interstellar gas is full of metals, and metals are extraordinarily good at one specific job. They radiate away heat. When a cloud of modern gas tries to collapse under gravity to form a star, the metals dump heat into space. The cloud cools, the cloud fragments into smaller pieces, and you end up with a wide range of stellar sizes, including small ones like our Sun. Pristine gas, gas with no metals, cannot do that job. It cannot cool itself efficiently. So when a cloud of pure hydrogen and helium starts to collapse, it stays hot. It stays massive. It does not fragment as easily, and the stars that finally ignite at the center of that collapse are not modest. They are not sun-sized. The first stars were giants. Most of them, according to the models, were between 10 and 100 times the mass of the Sun. But some may have been even larger. They burned so violently that they lived for only a few million years before exploding. In some cases, collapsing directly into black holes without an explosion at all. These were the engines that ended cosmic darkness. And here is where the second 2026 paper comes in. When Elke Ruster and her team at the University of Florence ran the Hebe data through their stellar models, the result was striking. The strength of the helium signal, the ratio of helium to hydrogen, the absence of metals, all of it pointed in the same direction. The mass distribution of stars inside Hebe was top-heavy. Most of the stars in its brightest component had masses between 10 and 100 times the Sun. Exactly the range theory had predicted decades ago for the very first generation. And the total mass works out to around 20,000 solar masses, a modest cluster by any later standard. But every star in it is a kind of object cosmology had only ever simulated, never observed. 500 million years after the Big Bang, in a universe that had barely built anything, the first generation switched on. And now, for the first time, we can see them burn. Now here is where the story turns. When the new JWST observations came in at higher resolution, the helium signal that had looked like a single source in 2024 turned out to be two sources. Two distinct components inside Hebe, both glowing with helium, separated by a small gap. The team labeled them, with characteristic astronomical creativity, C1 and C2. C1 is the cleaner case. The model fits there are sharp. The metal upper limits are tight. In everything in the data points to C1 being a purely population 3 system, a clump of pristine first-generation stars that has not yet enriched its surroundings with anything heavier. C2 is more interesting. The helium signal there is also strong. The metal lines are still absent within the limits of detection, but the ratios suggest something subtly different. Some models can fit C2 as another pure population 3 system. Other models suggest something more provocative. C2 might already have begun to transition. The first dust, the first traces of metals, the first evidence that one generation of stars has finished and the next generation has begun. If that interpretation is right, Hebe is not just a snapshot of the first stars. It is a snapshot of the moment the first stars finished and the second generation began. Both stages, and side by side, in a single object, captured by a single instrument, in a single observation. That kind of timing is almost unfair. To find the first stars at all would be a once-in-a-career discovery. To find them in the act of finishing, with their successors caught in the same frame, is the kind of thing astronomers usually only get to construct in simulations. And here it is, sitting in real data. The team is honest about the uncertainty. There are alternative explanations for C2 that they cannot fully rule out yet. C2 could host a population of metal-poor Wolf-Rayet stars that mimic some of the same signatures. It could harbour a small, accreting black hole. It could even be a direct collapse object that bypassed the normal stellar phase entirely. Each of these is harder to fit than the population 3 interpretation, but none can be eliminated until deeper observations come in. More JWST time on Hebe is already being scheduled. Step back for a moment. For most of human history, when we looked up at the night sky, we were looking at a curated selection of cosmic history. Mostly nearby stars, a few distant galaxies, a small slice of the universe, edited by what is bright enough to reach us across distances we can barely conceive of. Everything we knew about the first stars was theory. Models, equations on a whiteboard, numerical simulations running for weeks on supercomputers. Beautiful, in their way, internally consistent, but fundamentally guesses about a chapter of cosmic history that no instrument had ever read. We had built a whole story about how the universe lit itself up without ever seeing any of it happen. Hebe changes that. And if the interpretation holds, and the broader astronomical community is cautiously optimistic that it will, then for the first time in the entire history of human astronomy, we have a direct observation of the kind of light that lit the universe out of darkness. Not the descendants of those stars, not their echoes in the chemistry of newer generations. The actual stars themselves, frozen 13.4 billion years in the past, sending us photons that took longer to reach Earth than the Earth has even existed. The story of cosmic dawn is no longer hypothetical. It is data, a spectrum on a chart, a handful of pixels in a deep field, a pattern that matches what theory said it should be, found in exactly the place theory said it should be found. The next few years should bring more, and other population 3 candidates have been suggested in older galaxies. None of them have the full set of fingerprints that Hebe shows, but with deeper JWST surveys planned, with the Roman Space Telescope coming online by the end of this decade, with extremely large ground-based telescopes opening their domes in Chile and Hawaii, the population of confirmed first-generation systems should grow from 1 to 10 to dozens. Cosmic dawn is becoming visible. For 13.8 billion years, the first stars existed only in theory. Then JWST pointed at a small smudge of light next to a galaxy that has been there for almost as long as the universe itself, and one of the oldest stories in physics finally turned the page. The ghost stars are real. We can see them now.